Welcome to the deep dive. Today, we're plunging into some source material that's, well, it's incredibly specific, almost bizarrely so, but really quite elegant. We're talking about walking. Human gait, but with a very particular setup, analyzing what happens when you walk holding two specific geometric shapes. An acute golden rhombohedron in one hand and obtuse one in the other.
Yeah, it sounds a bit out there, doesn't it? Our source is a draft paper, academic stuff, building this whole framework. It connects geometry, pure shapes, with biomechanics, how we move, and even operator theory from math and physics.
Right, and the question it's tackling is pretty deep. It's not just asking, do these add weight? It's asking how these shapes, which are built around the golden ratio, phi, how they actually change the dynamic algebra of your movement.
Exactly. That's the mission for this deep dive.
Yeah.
We need to get past just carrying stuff. We have to look at coupled inertia, how these things resist motion together, and this idea of non-commutative algebra. Sounds complex, but bear with us.
Yeah, because the crucial bit seems to be why the order matters. The order in which these things affect how you move, and how this golden ratio, phi, isn't just sitting there in the shape's dimensions, but it actually dictates the asymmetry you feel every step.
It's the key scalar, yeah.
Yeah.
Governs the whole thing.
Okay, so it definitely sounds more like applied geometry than just a study on walking. Let's start with the shapes. Golden rhombohedra. Why these specific ones? What makes them so special?
Well, their origin is interesting. They pop up in quasi-crystalline geometry. Think of structures that have order, definite patterns, but they don't repeat perfectly like a simple crystal. A bit like certain tile patterns, Penrose tiles, maybe.
Okay, so ordered but not rigidly periodic.
Right. And because they're golden, their dimensions, the edge lengths, the angles, the face diagonals, they're all tied together by the golden ratio phi. That's roughly 1.618. So you have the acute one and the obtuse one, different shapes, different ways their mass is distributed internally, different principal axes of inertia, but they share this deep connection through phi.
And when you put one in each hand, boom, you've coupled them. Linked two things that are related geometrically but different mechanically.
Precisely. They become a single system interacting with your body.
And the paper models how this changes your effective inertia, right? Basically, how much harder it is to rotate your arm around the shoulder. It uses the parallel axis theorem, which accounts for the object's own inertia, plus the effect of holding it out at arm's length.
Exactly. And here's where the geometry really starts to show its hand numerically. The source uses some typical estimates, say the shapes have an edge of about 8 centimeters, and your arms may be 70 centimeters long.
And the numbers they calculate are quite different. For the arm holding the acute rhombohedron, the effective inertia is about 0.2385 kilogram meters squared. But for the obtuse side, one honor, it's noticeably less, about 0.1472 kilogram meters squared.
Yeah, quite a difference. And if you just take the ratio of those two numbers, the obtuse inertia divided by the acute inertia, focusing on the main axis your arm swings along.
You get roughly 0.62.
Which is
1 over phi, the inverse of the golden ratio. Wow.
right. So the geometry of the shapes, combined with holding them, forces the inertial asymmetry of this whole system, plus the objects, to map directly onto this fundamental constant.
That's pretty profound, even before we talk about actually walking. Just holding them sets up this perfect phi-based imbalance.
It really is. That's the defining scalar ratio for this setup. The paper makes a strong case that this $1 Varfa thing is physically baked into how these specific objects couple to you.
Okay, that setup leads us to the next big conceptual step in the paper. We've got this static ratio, $1 Varfa, but walking isn't static, it's dynamic. So we need to move from just numbers to inertia tensors, J01 jollers, Y tensors. Why the more complex math?
Well, a simple number, a scalar, just tells you how much resistance there is overall. A tensor tells you how that resistance changes depending on which way you try to move it. Direction matters.
Like trying to twist something versus just pushing it.
Exactly. When you walk, your arm isn't just a simple pendulum swinging back and forth. It's rotating, twisting slightly, changing angles in 3D space. And the critical point is that the acute and obtuse shapes have different internal structures. So their principle acts as the natural directions of easiest and hardest rotation. They don't line up when you hold them naturally.
Ah, the misalignment.
That misalignment is the source of the non-commutativity.
Non-commutativity, where A times B isn't the same as B times A. So algebraically, their commutator isn't zero. Joe Jollers is not zero. How does that math translate into, the actual feeling when you're walking? For someone not deep in tensor math.
Think about your muscles. When you swing your arm forward, your shoulder muscles have to generate torque to overcome the inertia. Now, if your body sort of compensates for the acute shape's inertia first, and then the obtuse shape's inertia kicks in during the next part of the swing,
Correct.
the total rotational effect, the twist felt by your torso, is different than if the obtuse influence happens first, followed by the acute.
So the sequence changes the outcome.
Precisely. The order of how the inertia engages, how the angular momentum contributions stack up, it determines the dynamic result. Your body can't treat them the same because the geometry forces this order dependence. You literally feel a different sensation based on which influence dominates first.
That makes sense. It grounds the math in a physical feeling. And this leads directly to the four operators the paper talks about, right? Combining these tensors creates operators that map to specific feelings during the walk.
Yes, 4 distinct dynamic signatures.
Okay, the first one. The ratio operator, toward all equal, is JJ1. It measures the mismatch. The paper says the perceptual effect is that the acute hand feels lighter and more reactive. Now that seems odd because we just said the acute side has higher effective inertia. Why lighter?
Yeah, that's a great point. It seems counterintuitive. But the ratio operator isn't just about the total inertia value. It's about the relative ease of initiating change along specific directions.
No.
The acute shape, due to its geometry, actually offers less resistance to acceleration along the primary swing axis, even though its overall inertia might be higher if you consider all possible rotations. So R highlights the difference in responsiveness, not just static mass. It resists certain twists more, maybe, but it's easier to get swinging.
I see. Responsiveness versus just raw inertia. That's a key distinction.
Yeah.
Okay, what about the sequential operators, the product ones? Pi p equals jaw. That's acute influence followed by obtuse.
Right. The paper describes the feeling for pilers as something like a stabilizing broad drag followed by a quick correction. The initial phase is dominated by the acute's responsiveness, maybe feeling broad, and then the obtuse side's influence results in a sort of corrective feeling later in the swing.
Stabilizing brag, then quick correction.
Okay.
And because it's non-commutative, the reverse sequence, pull up yaw, obtuse, then acute, must feel different.
And it does, according to the source. Perez is described as a destabilizing jerk followed by a braking effect. Here, the obtuse influence comes first, maybe causing a less predictable initial motion, a jerk, which then needs the different inertial profile of the acute side to sort of decelerate or brake it.
Wow. So the fact that people apparently feel these distinct sensations consistently, it really confirms you're physically experiencing non-commutative algebra. 1 out times b feels different from bow times all.
You're basically a walking, talking demonstration of it, yeah.
Okay, let's move to part 3. How does this whole coupled system behave during normal walking? The paper frames this using Hamiltonian mechanics.
Right, that sounds heavy, but the idea is pretty straightforward. A Hamiltonian is just a function that describes the total energy of a system, kinetic plus potential.
Okay.
When we say the body acts as a time-dependent periodic Hamiltonian, it just means your walking involves a repeating cycle of energy changes, like clockwork almost. The frequency is your gait frequency, maybe 1 to 2 steps per second.
So it's a system being driven periodically.
Exactly, which puts it in a class called Floki Hamiltonians. But the important thing is this framework lets us make some very concrete, testable predictions about your walk.
And the most direct one seems to be about how far your arms swing, the amplitude.
That's right. Remember that ratio of effective inertias, y owned by ls is y622 or $1 Verfii?
Yep.
The paper predicts that if your torso applies the same amount of torque, the same muscular effort to swing both arms, then the resulting angular accelerations should follow that same ratio. So alpha alpha should also be about 0.62.
Meaning the arm holding the acute rhombohedron will accelerate less for the same effort. So its swing amplitude, it should be smaller, reduced by almost 40% compared to the obtuse side.
That's the prediction. A significant measurable difference. You could literally strap simple motion sensors, like IMUs, to your wrists and look for that 0.6 amplitude ratio.
That's a very clear consequence of the geometry.
It is. And there's another effect. The total inertia added to your system arms plus trunk increases overall. This tends to lower the natural frequency at which your torso wants to rotate. You might feel like you have to work a bit harder, put more energy in to maintain your usual walking speed or cadence.
Right, makes sense. More mass, slower, natural swing. But then, here's where it gets really interesting, where that $1 Verfii ratio seems to flip from being a sort of deficit to an advantage. The transition point, going from walking to running.
Ah, yes, the bifurcation regime. That walk-run transition is a classic area in biomechanics. It's the point where walking just becomes less efficient energetically and your body naturally wants to switch to running. The source models this critical point mathematically, linking it to a specific frequency, 5 hours.
And what happens at that frequency?
This is the really cool part. The math suggests that as your movement frequency approaches this critical transition frequency, 5 hours theory, that non-commutativity, we talk about the dollar, Jonah-Cadola thing, actually starts to diminish. Mathematically, the commutator approaches 0.
So, the A times B versus B times A difference, it fades away. The system becomes more commutative near the transition.
Exactly. It smooths out algebraically. And physically, what that means is the internal interference, the conflicting torques generated between the two arms because of their different inertial responses, gets minimized.
So the system synchronizes itself.
Precisely. It self-synchronizes. And when this happens right at that optimal point, the walker perceives a sudden, noticeable drop in effort. It's that feeling when you just click into the perfect stride, what athletes call flow, or being in the zone.
So the golden ratio, phi, isn't just defining the static imbalance. It's acting as a kind of target, a dynamic attractor for efficiency.
That's exactly how the people frames it. Phi acts as a dynamic attractor in the phase space of how you move. Your body, trying to be efficient, unconsciously tunes your stride frequency towards a state where the dynamics related to phi minimize energy loss, minimize that internal wrestling between the arms.
And the feeling of flow is the subjective experience of your body finding that efficient algebraic solution guided by phi.
Yes, you're embodying this optimized state driven by the geometry you're carrying.
Okay, this leads us into the final section, part 4, which is maybe the most speculative part, but also deeply fascinating. It makes a leap towards philosophy, even psychology. The paper coins this term, inertial eigenforms. What do they mean by that, eigenforms?
Well, eigen usually means something characteristic or inherent. They're defining these rhombohedras as special kinds of portable geometries. Their defining feature is that the complex inertial algebra, they create that non-commutativity, the phi ratio, it's directly perceivable. You don't need instruments, you feel the math in your body.
You feel the structure.
Yeah, they argue these shapes create a unique, repeatable torsional beat or rhythm in your gait cycle, directly linked to phi. You're feeling a structured pattern.
Okay, inertial eigenforms geometries you can feel the algebra of.
That's the core idea. And this is where they make the connection to analytical psychology, specifically to Carl Jung's idea of synchronicity.
Synchronicity, that's the idea of meaningful coincidences, right? And a causal connecting principle, Jung called it. How does that connect to walking with funny shapes? We just jump from biomechanics to Jung.
The bridge is the meaningful pattern. Synchronicity, in the Jungian sense, isn't just random coincidence. It often involves relating an external event, here, the specific geometry of the rhombohedra, with a distinct internal experience, the feeling of flow or that torsional beat, through some underlying shared principle or archetype.
And the shared principle here is?
The golden ratio, phi. The source proposes that phi is acting like a physical archetype, a fundamental, universal organizing principle. It organizes the physical world, the shape's geometry, in such a way that it directly manifests as your psychological perception, your felt sense of movement, especially that feeling of effortless flow.
Physical archetype. That's a powerful idea. It links the math and the object to the feeling in the person.
Exactly. And it resonates with the later work Jung did, particularly his collaboration with the physicist Wolfgang Pauli. They explored this concept of the unus mundus, a unified reality where the physical world and the world of the psyche mind are just different aspects of one underlying order.
So holding these rhombohedra isn't just a mechanical exercise. The argument is that it's an embodied experience of perceiving a deep, structured, maybe even archetypal pattern inherent in the cosmos, made tangible through these specific forms, experiencing physical synchronicity.
That's the essence of their conclusion, yeah. It's quite a leap, but it follows logically from the physics they lay out.
What a journey. Okay, let's recap. We started with these two, let's face it, pretty weird geometric shapes, golden rhombohedra.
Definitely niche.
And we found that carrying them imposes this really specific non-commutative algebraic structure on the simple act of walking, where the golden ratio, phi, pops up everywhere.
Right. It acts as the static asymmetry factor, that 0.62 ratio in inertia and swing, but also as this dynamic attractor guiding the system towards peak efficiency, towards that feeling of flow near the walk-run transition.
And importantly, this isn't just abstract math theory. There are concrete, testable predictions.
Absolutely. That arm swing amplitude difference, the 0.6 ratio, that's something you could check relatively easily with modern sensors. You could verify if the acute arm really does swing less, just as predicted. It's empirical science.
The physics is testable. The philosophical interpretation,
Well,
well, that's more interpretive.
naturally. But the link is there in the math and the predicted perception.
So, the real power here is that connection between abstract structure and felt experience, which leads us to the final provocative thought for you, the listener, to maybe ponder. If holding these very specific geometric objects lets us directly feel, directly perceive an ancient and fundamental mathematical principle like the golden ratio just by walking, what other abstract principles, what other kinds of order might be quietly structuring our everyday embodied experience? Patterns that are always there, but we just haven't found the right objects or the right framework to notice them yet.
Makes you wonder, doesn't it? Perhaps the world, and our experience of it, has a lot more hidden structure than we usually assume.
Something to think about on your next walk, maybe. This has been The Deep Dive. Thanks for joining us.
See you next time.